I speak about matroid matching, and especially the case of the oracle model. That is, the matroid rank function is given by a black box, and so we don't have the linear representation. Earlier approaches needed the linear representation. That's why. So there's not so much of new result that I will mention. It's more like issues. So let me repeat what the definition is. So there are some equivalent ways to introduce matroid matching, and so this one is with a two-polymatroid function. It is a set function that has non-negative integer values called a two-polymatroid function, because we have things like this for the matroid rank function, so that the empty set is 0 for any pair of subsets x and y that are, one is subset of the other. We have this monotone increasing inequality and the submodularity. Then for every singleton set that has only one element, the rank is at most 2. So that's a two-polymatroid function. We could get one just by multiplying a matroid rank function by 2, or adding two matroid rank functions on the same ground set. That also gives us a two-polymatroid function. Now, matching is a subset of elements for which the rank is equal to twice the cardinality. And this is an interesting definition, because usually less than or equal inequality holds. So when there's equality, then it's called a matching. Less than or equal to holds because of submodularity and the singleton rank at most 2. So the matroid matching problem, which was introduced nearly 40 years ago by Lovász, so I think he already introduced a few equivalent definitions. One is that given a two-polymatroid function, find the maximum cardinality matching. So this problem, the motivation was that there are several known problems that are special cases. So it's a common generalization of graph matching, when this defines the rank function. So the rank of a subset of nodes, a subset of edges, is defined by the number of nodes that they span. This is submodular, and the problem that we get is the maximum matching problem in that graph. Similarly, we can get the matroid intersection problem as a special case by just adding the two rank functions of the two matroids on the same ground set. So we can add them. That is a two-polymatroid function, and then a matching will be a common independent set. So this way we can get matroid intersection. So these are the two things that for which there are not so many common generalizations, and matroid matchings is motivated by this. Now, the linear matroid matching is the number 3 special case when we have a linear representation like this, so that we have the notation is a little, so I use V and E as before, E as before for the ground set, but we have a vector space V. So V now is a vector space. And E, for every element of the ground set, we have it is represented by a rank 2 subspace of the vector space. And so the rank function is defined just by taking the union's rank. When we have this kind of a representation of the set function f, then f is called a linear 2 polymatroid function. The reason that we consider this special case is because it is one of the polynomial time solvable cases. Lovász proved just a short few years after the introduction of matroid matching, he proved that this can be solved by there's an algorithm and there's a min-max formula like this. There's just a little issue with this. All this you can do in any field. You can do small fields or large fields. The issue is actually related to this. So the issue with Lovász's result that we really need linear algebra. So in this min-max formula, there is a so the minimum is taken over a partition pi that is the combinatorial thing. It is a partition of the ground set into any number of subsets and a subspace of the vector space. So this is a subspace. If the vector space is over a large field, then maybe the representation of K is hard to find. So it is not, K is not spanned by, it is not given by elements that we know from the representation. Maybe it is difficult to compute. So when you do Lovász's algorithm, this K comes from, you take intersection of some known subspaces and then generate elements and take the union, and repeatedly you do that. So in the end, maybe K, the subspace K, you need the matrix representation, and you need to do a lot of matrix computation in order to get K, and also in order to run Lovász's algorithm to prove this min-max formula. So by the way, the formula here, we have the rank of K, and somehow this other part where we take parity into consideration. In a way, this is similar to the Bärstadt formula for graph matching, where this would be the cut set X, and this would be taken over the components that we get.
Does visualize that? Can I just ask another maybe dumb question? I mean, so here your ranks, what you mean is dimension. So what do? You project these E's into the quotient space? Yes? No?
Yes.
Okay.
Yes.
All right, and right, okay. So by rank here, you really mean that these E's are vectors.
Yes.
Quotient, you look at the quotient space being like K, you project them orthogonally or so.
Yes, exactly like that.
And then you compute dimensions.
And the thing is that we cannot do this in the oracle model. In the oracle model, we would only have the rank function, right, but not the linear representation of these subspaces. We can end up with this subspace K from the representation. And at some point, I wanted to mention what would be, maybe there is a matroid or polymatroid that has a linear representation, but it is ugly. So we cannot do all this linear algebraic approach. And let me do this now. So it's just, so this is vector space V. Okay, V. These are rank 3 subspaces, okay? And then I take generic hyperplane. So it is dimension 1 lower than V, and it is generic in the sense that if this V would be over Q rationals, then the generic hyperplane would be generated by some transcendent irrational, some really bad numbers, so that all these intersections that we get will have rank 2, and then in this hyperplane we get a linear representation of some tuple matroid. So what we get here, it is a linear tuple matroid, but it is ugly. We cannot do Lovász's thing or any other known algorithm. And actually, this kind of, you can do this with a matrix, but then the intersection with the generic hyperplane will be done by introducing indeterminates in the matrix, which is a bad thing. Then you cannot really do linear algebraic computation computationally. So then there's a list of known results. Quite early there were hardness results. So for arbitrary matroids, there are only some approximation algorithms. For general, there is a 2/3 approximation and Petas later. And linear matroid matching, when we assume that the input matroid is given by a linear representation. First algorithm by Lovász. And then there are some, so Gabow and Stallmann, that's a completely different approach. And Orlin and Vande Vate is a third completely different approach. And there's Chong, that's the last one that comes from a linear algebraic approach, and it is a randomized algorithm. It is faster than both these approaches. So the fastest deterministic is Gabow-Stallmann and Orlin. Both of them are fastest, but Chung is faster by order of n. There's quite a lot of applications other than graph matching and matroid intersection. Let me mention just a few of these on the blackboard. So Mader disjoint paths, that is, input is a graph and a subset A1, A2, AK of nodes. So here within the graph, we have these disjoint sets, A1, A2, AK, and we want to find maximum number of fully node disjoint paths that connect. Each path will have to connect two different sets AI, and they have to be node disjoint. We want to maximize the number of paths. Schreiber determined a linear matroid matching problem that is equivalent with this one. So this nicely reduces to Lovász's theory. then is a then there is triangle cactus. We have 3 uniform hypergraph. That's the input, and the goal is to find something that in many ways is like spanning tree. So it is supposed to look like this. That there is no cycle. Somehow these triangles are connected with only one node. And the problem of finding a spanning triangle cactus is equivalent with doing matroid matching in the graphic matroid of, well, the complete set. So if you remove, if you represent one triangle by a pair of edges like this, and so on, then the thing that you get is a spanning tree. So the problem is equivalent with matroid matching in the graphic matroid. So Ligeti did combinatorial approach for this one, so that now we don't have to do linear algebra, but there is Zoli's combinatorial approach. There's a few other ones, but I don't want to spend too much time with this. There's some generalizations, and the most astonishing generalization is to linear delta matroid parity when we do delta matroids instead of matroids. And there's another way to consider fractional relaxation of matroid matching. It is a non-trivial thing, and currently the nicest result that there is so we can do this fractional matroid matching thing that's due to Vande Vate. With Dion Heisweit, we looked at the weighted problem, but then you can go one step further to submodular optimization over some. I'm sorry. Some lattices. I forgot the word. Submodular minimization over some lattices, which is quite interesting. And actually, this fractional relaxation is equivalent with something like that. It's a quite new and nice result. Tamás Király and some Japanese researchers did that last year. Okay, and there's the weighted matroid matching, but I don't want to speak about that. That's another talk. So, as I mentioned, you can do ugly representation, and there is a combinatorial problem for which we don't know the solution because it only has an ugly representation. This is the problem. Input would be an undirected graph. And the question is, does it admit an orientation that is strongly connected, and so that every node has an even in degree, an even number of edges oriented toward that node? So because of orientations of an undirected graph that in a way translates into a polymatroid, basis in a polymatroid, and parity translates into matroid parity. But then the representation that we have for this polymatroid is like this. It's ugly. So this is more or
even could be replaced by given parity there, right?
What?
So you can replace even by even or large.
Yes, yes, a prescribed parity, yes. So this, in a way, reduces to Lovász's min-max formula, but that is computationally infeasible because we have to do linear algebraic computations in this kind of ugly representation, and it somehow goes away exponentially, somehow, the indeterminacy in the matrix.
You would get some numbers in your matrix that would give exactly the right ranks on all subsets. And so
You can do that, and there is a randomized approach.
So you're considering this randomized?
Randomized has already been considered, and it works.
Okay, so no, I was asking this. So you're considering what I described as a randomized algorithm because I had to pick random bases.
So if it is on over rationals, and then you can go to random rational numbers for the indeterminates. Okay. Most of the time you can do that. If we know an indeterminate matrix, maybe if you do oracle-based approach, then it generalizes to a larger class of matroids also. I would hope for that. I don't know yet.
So the problem you stated there in red is the complexity open?
I think it's. I would say it is settled by something that is out there, but it is settled by Gabow Stallmann algorithm. If you look at it really smart.
You think so, but
But the thing that is written by Gabow and Stallmann or any other algorithms, that doesn't work. Those approaches do need the representation.
So this is not written anywhere that this polynomial is solvable?
No, it's not. No, it's not.
But
that's the issue, yes.
But Lovász's formula gives a good characterization, so it's a
No, it's not a good characterization. It's a characterization, but not a good one.
So it's not, so some part of the formula you can't check.
Yes.
Like
that does not imply that it is in P intersect NP.
So
NP intersect co-NP.
It is not black and white known that it's in NP intersection co-NP.
No, it's not. No, it's not known. So that's the issue. It is supposedly solved, but it's not really solved. That's the issue. So the thing is that in Gabow Stallmann's paper, there's a lot of linear algebra. When it continues with an alternating path, like in Edmond's matching algorithm, then it always intersects that subspace of rank 2 with something else and generates some new elements and then combines that with already known elements. So there's a lot of linear algebra in this paper, but what we would need is to translate this into combinatorics to see what that is. And so apparently there's a few really smart people that looked at this, including Satoru Iwata and Jim Gillen. So they would not bother looking at this anymore because they understand it as something that you can do with only knowing the rank function. But it's not obvious what is done in this paper. It does linear algebraic computations, but so I was trying to decipher the combinatorics behind this. So let me try to explain what's going on if we would only use the rank function oracle and not the matrix. So I would tell something that is like the translation of Gabow and Stallmann. So if you have a two polymatroid function, then you can define this polyhedron that where a subset is bounded by the rank of that subset. So xz is the sum of variables in z, and so this is a two polymatroid. It is a nice one because it is an integer polyhedron. 0, 1, and 2 will be all the entries in a basis. So two polymatroid matching is equivalent with finding a basis of this two polymatroid with maximum number of 2's or minimum number of 1's. That's not quite. So I should. Okay. So we want to consider a basis. We start with a basis and want to improve it. Like in matching algorithm, we start with an arbitrary matching, and we try to augment. And to augment, we would want to find an alternating path, and an alternating path in this environment looks like this. Like it's a sequence of in the ground set. I would just reorder the entries so that it looks nice. It would be start with a 1 and 2, 0, 2, 0 alternatingly. That's an exchange path, and the main thing in this definition is that these are all different entries, so the 0 will not repeat later. So the length is bounded, and when we do the exchange, it is a basic exchange. If this one has also to be feasible if we do exchange between first and second element, and if we go then at the second step we do exchange, that also has to be feasible, and so on. If we do these exchanges as a sequence, then we get that many bases. That is the definition of exchange path, and so the idea is that we want to reach another element 1, but that's not so. We will. There's the difference between this thing and Matroid intersection algorithm or graph matching algorithm of Edmonds is that here we don't look at the underlying graph. Usually there's a graph, but here we discover the graph by trying to extend. If we already found an exchange path, then we want to go one further. And the way we want to go one step further is with breadth first search. So that's how we do. We first want to discover all the exchange paths of length 1, and then we try to extend all possible ways to exchange paths of length 2, and so on. That's what we do. But there is no graph. Somehow the structure gets discovered on the go. So we find, if we start with this 1, then we discover this structure, arborescence, rooted in a 1. And then actually we do this simultaneously, starting with all the 1s as roots. And then in the end, we will try to connect 2 of these arborescences so that we get from one of the 1s to another 1. And then we augment on this path. That is what we do If we find a connection like this that is feasible, then we are happy. And actually, this, what I already explained, would solve matroid intersection in an oracle model. But, and there's a related thing. By the way, doing matroid intersection with oracle model like this, the sum of the two rank functions, it is easy to see that it is equivalent with matroid matching, but I don't know any other approach that would solve matroid intersection just from this oracle. It follows from this approach, but not from the earlier theory. And by the way, this would be solved for any two matroids. They don't have to be linear in this case. A related result, as a remark, let me mention that Mihály Bárász looked at a case when we only have one oracle for matroid intersection that is the minimum of the two rank functions. And so that's also a sufficient description of matroid intersection problem, because we have an independent set, a common independent set that is that means that with this set function, the minimum, it is also easy to see that it's a common independent set. So the matroid intersection is well defined with this oracle also. And Mihály Bárász discussed the Edmonds algorithm can be implemented with only this oracle. There's just little things with, so the main idea is that the augmenting paths from Edmonds' algorithm, we don't have the auxiliary graph. We have another auxiliary graph based on this oracle, but the two graphs in terms of breadth first search are equivalent. So the difference is only edges which don't have an impact on breadth first search. So, but for this other oracle, I don't know such a. I think that's not true. So we cannot reconstruct Edmonds' auxiliary graph from this oracle. So that makes this thing interesting. And okay, so but for matroid matching, linear matroid matching, if we need to do something a little more, Gabow and Stallmann's approach would do blossoms. A blossom looks like this. We went this far and that far with breadth first search of exchange paths, and then we find that this element, there are two different ways to reach it by a shortest, in the following level of breadth first search, and then this becomes a blossom. Actually, so a blossom will look like this. There is the definition of a blossom is that if we go this way all the way around, or that way all the way around, those are exchange paths, and that this whole thing needs to come from breadth first search. That means that there is no cross edge. The set of a blossom actually is only this part. It doesn't include this is called the tip. No, it's called I always mix that up. It's called tip, or it's called tip or bud. I always mix the two up. So this one is the tip. This is the bud. Does that make sense? Okay. Yeah, anyway, so that's the. I
Two native speakers, I see. I don't know why.
and then we will discover this kind of structure, an arborescence, but all kinds of nodes are somehow pseudonodes that come from blossom, and we don't really shrink them. We need to memorize those exchange paths that we start here from the root, and we memorize all possible exchange paths that go inside, and then one of them can be extended outward, and we need to try all those linear number of possibilities. So how then a new blossom is formed like this. We reach, as I said, but we can still do this with blossoms inside, so it will be a nested structure. And then so it's just one blossom step. When a new blossom is discovered, then we need to try and look for further blossoms that are generated by this one, because maybe if we tried this way and we could not get there, so this did not become a blossom. But now we can go this way all the way around and then go there, which means that this whole thing here becomes a blossom. So we have to pick all those generated elements, and this way, in one go, we can grow the blossom like this. Eventually, this will stop, and then we go on with breadth-first search and blossom search. So, okay, we get this kind of structure, just multiple of these arborescences, each element with a 1 is the root of another arborescence. And then somehow there's a way to determine, if there was a linear representation, there's a way to find the set K from Lovász's min-max formula, and the partition pi, it just comes from the partition that we had in the last, so the largest blossoms and all the remaining elements by themselves. So that's what proves correctness. And then I think this is my last slide already. So that was Gabow and Stallmann's algorithm described only with rank function oracle. But somehow we can do this algorithm, but we don't get a certificate. It is like implicit in the proof. Can we do this for the weighted problem or delta matroid matching? And there's the questions for R1 plus R2. How can we, is there a way, for example, to describe the common independent set polytope for matroid intersection in terms of R1 plus R2? I don't know how you can do that. R1 plus R2 determines that polytope, but I don't know how to find a nice description. I don't know if it has quota rank 1. If we would do the take a rank of a set and round down to the closest even number. I don't know.
You can describe the intersection polytope in terms of the sum of the two main functions?
No.
Oh, I thought you said that you can describe the polytope.
It determines, but I don't know how you can. So it determines, but it's not me determining. It's conceptually it's determined, but I don't know a description. And maybe there is one. I don't know.
But you mean conceptually? You mean the original description with R1 and R2? That's
Yeah.
what you mean by conceptual.
Can I ask a question?
Sure.
So what you so the common independent subtotal algebra, if you have minimum R1 and R2, you just say over all the subsets.
Yes. That's
Right. Okay. And so now you're asking, can you make the right-hand side be not in terms of minimum, but in terms of plus?
yes. So a valid inequality would be for x, z is less than or equal 1/2 of fz rounded down. So this is a valid inequality. And if you consider them and take the integer hull, you get back the common independence at polytope. But so that's integer programming description. But does this one have quata rank 1? I don't know. Maybe. Thank you. Thank you for your time. Yes?
Your orientation problem fits into one of these.
So this is what I said would solve the orientation problem.
What you said about what?
All this thing. This is Gabow Stallmann's algorithm, only described without linear algebra. This, if you do this solves the orientation problem, the problem number 4 or something like that. So this problem is solved in this way by Gabow and Stallmann. It's just not put that way in Gabow Stallmann. Mm.
Where did you use linearity?
In the proofs that I did not,
Oh, okay.
that are in Gabow and Stallmann's paper. In the proofs you can do linear algebra. In proof of correctness for the algorithm, you can do that.
Okay. Okay. So really, the proof of correctness relies upon geometric arguments.
Yes, but there are certain generalizations. For example, algebraic matroids. I don't know. I think nobody knows if this algorithm would also work for that. So there's a lot of little things that can be.
Well, again, over a sufficiently large field, yes. At least randomly, right? You can look at the modulus differentials of the algebraic matroid, and this is linear, right? Over some massive field, and if it's big enough, you can pick random numbers. Which is because I'm not very smart, so I know how to do it. I guess so then your algorithm will work again. Right, so for nice algebraic matroids.
There's a notion of linear matroids and algebraic matroids. Algebraic matroids is a larger family of matroids. That is not linear algebraic independence. Rather, it is like, Galois theory kind of independence.
You can basically take derivatives and linearize it, at least generically.
Maybe. Thank you.